First speaker today is Ayelet Lindenstrauss, and she's going to tell us about Tambara functors and equivariant versions of Loday constructions.
Thank you. And again, thank you for this conference. It's been great. Okay, so I'm going to start with just thinking about things. So say S is a spectrum a genuine H spectrum. But I don't want to talk about the details. I want to talk about the idea. I don't need any products. You can, and of course, G is a finite group, and H is a subgroup of it. So you have a genuine H spectrum. You can build a G spectrum. Again, not a little fussy about the details, but the norm from H to G of S. And what it's going to do is it's going to be the smash over GIH in G mod H. So you pick representatives G1H all the way up to G mod H, and you pick G1 equals E. So for each of these cosets, you're going to take a copy of S. And G acts on this as follows. If GIH, so it's some coset. If the way I chose to call this coset is GJH, then I move the S over GIH to B over GJH, but act on it by GJ inverse GI, which is an element of H. Okay, so this is a construction. And again, S did not even need a product. So I want to do that. And the point is that if I have SH, or I have something, I'm very informal. If I have something in S fixed under H, write it in every coordinate and get something fixed under G. Okay, exterior norm, classic idea. Okay, now, Hill-Hopkins-Ravenel did this in a modern way. So they defined a monoidal norm NHG from genuine H spectra to genuine G spectra on a point set level. That does that. And again, the spectra did not need to have any product. But if they do have a product, And for IH star, it goes from genuine D spectra to genuine H spectra, which restricts Am I supposed to talk about this? Restricts the action from G to H. Then if A is a commutative algebra in genuine H spectra, and B is in commutative algebra of genuine G spectra, this Hill-Hopkins-Ravenel exterior norm is a left adjoint of IH. We identify C-alg of genuine G spectra of NHGA to B is identified with C alg genuine H spectra of A IH star. So it exists even if you don't have a product. If you have a product, it's the adjoint of restriction. It's monoidal. It's a great thing. Okay. That isn't exactly where we left off yesterday, but I wanted to write it. What are we going to use it for? So I'm going to say something a little better than I said it yesterday. I'll say why in a moment. So our goal for a ring, so for a monoid, A in, or for, just for A in commutative algebra of genuine G spectra to be genuinely commutative is to define a notion of X tensor A for X G sets that is natural in X. And of course, we also want naturality in A, but that's cheap. Ever since I started talking, I talked about natural functors of A. So that's the easy part. So that means for all G set map X to Y, I want a well-defined map X tensor A into, oh no, sorry, these are not, nobody's simplicial. These are finite. They're going to be simplicial eventually. Right now, they're just finite. I want a well-defined map from X to Y in a way that respects in a functorial way. I want to respect compositions and identity. Last time I was just talking about, so you have X and it's a bunch of orbits, and you have Y and it's a bunch of orbits, and orbits of X decide where they go, like that. If I just knew how to map from any G set X into any orbit, I'd be set. Yesterday I said I wanted to map only into the trivial orbit. That was what I forgot. But anyway, the easiest way is to say it like this, rather than say, okay, for each orbit, I want to know that if I have a general G set that I map into the orbit, I know how to do the multiplication. And then the G isomorphisms of X is something that should commute with the map from X to a point. So it's all in the functoriality. So this is the correct way, because I'm not ignoring the orbits to say what I wanted yesterday. If I can do this, I said it that way to look more like commutativity in the non-equivariant case. But this will be genuine commutativity. This is what I'm after. Okay, so yeah. So if I have a, and remember we said in the non-equivariant case, if I just have a finite set and I take a copy of that many, I mean, a smash of that many copies of A, I'm going to call that the finite set, tensor A. Okay, so this is what we want. So the question now is, what should G mod H tensor A be? And then the second question, okay, we'll talk about it in a moment. First question is, what should that be? So it seems like non-equivariantly, this set has this many elements. Non-equivariantly, I should have that many copies of A. Now, presumably, when G acts on G mod H, it moves the cosets by the pattern I was writing about before. So it should probably move those copies of A, like I said. And then somehow H doesn't do anything useful here, so maybe, no, I'm sorry. And then G moves the copies, and then the part of G beyond H has already moved copies, so maybe it doesn't need to do anything, but maybe H should do anything. So the answer, I was trying to motivate it, I hope I succeeded. The answer is I take NHG of IH star of A. Hope I motivated it. Anyway, this is the definition. Okay, and then question, if I have X, Y disjoint G sets, seems like if I look at X disjoint union Y tensor A, because when I did the non-equivariant case, I just smashed over all the points. Well, if I have two disjoint G sets, the G thing really doesn't put them together in any way. So presumably I should have X tensor A smash Y tensor A. So hopefully the hand waving made you think these are reasonable definitions. But if I take these, if I do this, I've defined X tensor A for all finite G set X. But I haven't shown that it's natural. Okay, so what are the basic moves giving me all G maps of finite G sets? In order to do this, given a finite G set, I can choose a way of identifying it as GH1 disjoint union GH2 disjoint union GHL. There is a choice there. Like if you have a G set, well, it's clear what the orbits are. But if I want to write each of the orbits as G mod H, then I pick, this is X, and then this orbit looks like G mod H, where H is the stabilizer of this X. And here, there's another point here, there's another point here, there's another point, right? Once I take the G set, write it like this, then I can apply that, and then I'm set. But what are the different basic moves that I could do when I make maps of G sets? So I can include some G sets into X disjoint union G mod H. I can change, if I had G mod H times X to G mod GH G inverse times GX. So I had this orbit and I thought it was the orbit generated by X, but it could be the orbit generated by GX. But then of course the stabilizer changes. I'm not doing anything to the orbit. I'm just changing the way I look at it. Okay, I can collapse or fold two orbits that I've identified as G mod H, disjoint union G mod H. And I just can overlap the X of this one with the Y of that one and get a single one. Okay, and I can permute orbits. And maybe you're following along with me and thinking, oh yeah, I could do that in this definition. And then the last one is if K is a subgroup of H, I can quotient G mod K into G mod H. Okay, so these are my moves. And this is my definition. And the question is, what do they do? What do they do on X tensor A? Okay, I'm just going to say what they do. It also should be consistent, and that's a hard thing to check. But okay, so if I include this, I'm supposed to basically go from X tensor A into X tensor A smash G mod H tensor A This is the genuine equivariant G spectrum. It has a unit map. So you just copy and apply the unit map. You win. Nothing hard. Okay, here, basically you go from G mod H tensor A to G mod GHG inverse tensor A by CG. That's exactly what CG was built for. Here, you're supposed to go from G mod H tensor A smash G mod H tensor A. You're supposed to go from that to G mod H tensor A. Yeah, but this is a genuine G spectrum. It has a product. Easy. Permute orbits. Okay, so, you know, you have...
Now you are assuming A is permuted.
I am assuming that A, right. Yeah. I should have said, yeah, so it's clear. So I start with genuine G spectra. And no, and right, and I need the product, exactly. I start with genuine G spectra. I know that if I want something that's commutative, it should at least be a commutative object in genuine G spectra. So I am assuming that, and that's how I get the product. Thank you, yes. Yes. Okay, great. And then I can permute orbits. So I have disjoint union over some set S of G mod H's. And to it, I associate smash over S G H tensor A. So I want to permute the order here. I permute the order here. So these were all just so easy. They use the structure I had. Here, I guess I need a map from G mod K tensor A to G mod H tensor A. And what of the structures I've already seen gives me that? Well, nothing does. This is what I want. If I have this, I have a generally commutative spectrum, but I don't know how to do this. And the point is, if you have these for all K in H, and moreover, I want for all J in K in H and in G. I also want a way of going between H, J tensor IH star A into HK tensor IH star A. Same kind of thing. If you have this, in a way, that makes A and all the IH star A functorial. Genuine commutativity. And again, if you're just a commutative algebra and genuine G spectra, none of these need to exist, except for the stupid cases of E and G. And it is very possible that only some of them exist. I have to be a little careful about choosing which some of them, and there's a whole study of that. But it could be that none of them, some of them, all of them exist. And genuine commutativity means all of them exist. Okay. So now we know what genuinely commutative G spectra are. If we have such a product from G from H over K tensor IH star A into H over H tensor IH star A. And that's just a fancy way of saying A. And this is, we know what that is. This is NHK IK A. Okay, the standard notation. Basically, it's confusing here because there's inner norms and outer norms, and there's inner restrictions and outer restrictions. And traditionally, the G isn't here. Here, I mean restrict from G to H. Here, I mean restrict from G to K, which involved first restricting from G to H and then restricting from H to K. It's not in the notation, but that's what I mean. If I have such a product, then I get a new structure on pi 0 underline of A. I can go from AK into, I mean, I can take this and I can build NKH IK star. So I have, I have this. And as we talked about, if you start with something in A that's fixed, when you take the norm, you're going to get something that's fixed under H. But then you can apply this thing and end up in AH. So basically what you did, we mapped, okay. So we just mapped pi 0 underline A of K into pi 0 underline A of H by a completely different thing than transfer. And this is called norm, or some people just use a big N. It's important to distinguish it from the other one, but okay. So in addition to all the structures that pi 0 underline of A has, because A is a genuine G spectrum, and A is a commutative algebra in genuine G spectra. So, you have all the Mackey stuff and you have this green stuff. You just got a new structure. If A is a genuinely commutative G spectrum, and we don't say genuine anymore because it's implied, but this is the fanciest thing. Then this is something that Morten Brun showed. Pi 0 underline of A is a Tambera functor. This is again something that came from representation theory. So what is the idea here? T is a Tambera functor, a G Tambera functor, if it assigns for all H, G, a commutative ring T of H. And for all K in H, we want the things we had before, res KH from TH to TK, and this is supposed to be a ring homomorphism. And we have transfer K to H, and that goes from TK to TH. And this is supposed to be additive, but not multiplicative. And norm KH, and that goes from also from T of K to T of H. And this is multiplicative, but not additive. And for all G in G, CG from TH to T G H G inverse, and that's a ring isomorphism. And all these guys behave nicely with respect to compositions, and they behave in the obvious way with respect to conjugation. So basically, I want with all Mackey and green properties plus an analog of double coset formula for res JH norm KH. If you have two subgroups, J and K of H, just like we had for the transfer, plus distributivity of norms over transfers. So a whole lot of properties, but this is a Tambera functor. And that exactly captures what you get in the pi zero of a genuinely commutative G spectrum. The distributivity is a little complicated. I'm going to give an example, but before that, let me give an easy example of a Tambera functor to orient your thinking about this. So so it's an example. If B is a commutative ring with G action, obviously by G homomorphisms, by ring homomorphisms, I get a Tambera functor B fix, very much like we had for an abelian group with G action. And what does it do? B fix of H is equal to BH. And as I had before, res KH, it's just the inclusion of BH into BK if K is smaller than H, and transfer, and then I'm going to write H is equal to the sorry, is H1K up to H over K. So then the transfer KH of B is defined to be the sum over I goes from 1 to HK of HIB, and the norm KH of B is the product. I goes from 1 to H and K of HIB. Let's see, and again, since B is fixed under K, the representatives don't matter. And you can check that all this works, and you can begin seeing what kind of distributivity you're going to get. So I'm going to talk about distributivity only in the easiest case. Easy example of this relativity. So I'm going to take G equals CP and H equals E. So I'm going to take a CP Tambara functor, and then the result there is that norm ECP of A plus B is equal to norm ECP A plus norm ECP B plus transfer ECP of the sum over all the S non-empty contained and not equal to CP. And then I look at the product little s and big S of SA times the product little s in CP without big S of SB. Okay, so like if you think about this example, norm is the product of the conjugates. I'm just sort of using, right, I'm multiplying A plus S, A plus all the conjugates times B plus all the conjugates. So I'm taking a big product of these. So I have the terms that have only the conjugates of A. Great, that's the product of A's conjugates. Then I have the terms that have only conjugates of B. Okay, and then here I have all the guys that are mixed A's and B's. So that's an example. The combinatorics is complicated. And what Strickland did to make sense of the combinatorics, but it's still complicated because everything's, because I mean, it's a harder concept than Mackey functors. But Strickland, he says, consider the category with objects like we had yesterday. Objects is a small skeleton of the category of finite G sets, and morphisms from X to Y are all bispans. Oh, okay, right. Modulo obvious CP action. Sorry, that's what I'm taking the trace for. Thank you. Yeah. So then I look at all bispans of finite G sets like this. A, B, Y. So these are just diagrams of finite G sets like this up to homeomorphism fixing X and y. And G Tambara functors are product preserving functors from this category to sets taking value in abelian groups. You'd like to say that there are functors from this into rings, but it's clearly not true because I had maps that did not induce ring homomorphisms, so obviously wrong. The funny thing is, if you just say into sets, then you get the addition. This thing will give you the addition, it will give you the multiplication, it will give you everything but additive inverses. Oh, that's why we want the functions to get value in additive groups. And just to connect this to reality, so obviously, if I have such a functor, right, then f of G mod H, we can define as the Tambara functor SH. And then for K in H, there is just one thing we could do. We can map from G mod K into G mod H. And identities, of course. So how do we build bispans from this picture? Well, basically, we take this someplace and everywhere else is identities. So we could look at G mod H, G mod K, G mod K, identity, G mod K. This is a perfectly good, this is the identity as well. This bispan corresponds to res KH. And then I can also look at, this is the interesting map. Or I could take G mod H, take the identity here, and put the interesting map I know how to do. No, what am I doing? Sorry, G mod K, G mod K. My interesting map goes from G mod K to G mod H. So I do this, goes to G mod H, goes by 1 to G mod H. And this corresponds to norm HK. And then I can also finally do G mod K, G mod K, G mod K, and then do the interesting map here. And this corresponds to, if I have a functor, a product preserving functors F from the category. So I'm just saying how to view this in terms of Tambara functors. So this gives you res, this gives you norm, this gives you transfer. You see that I can, yeah. So the spans sit easily in bispans if you only make the top the identity. And this is in fact the composition in this order. And the combinatorics is hard, and I'm not claiming it's not. Okay, but we have the easy example. Oh, and I forgot to say, the Burnside-Mackey functor is actually a Tambara functor. A little harder to specify the product, but again, A is pi 0 underline of the genuine equivariant G sphere spectrum, which can be given a genuinely commutative structure. And again, A is the initial Tambera functor. Okay, so now Tambera functors have been better specified, and I'm going to move on. But in the process of doing that, note that we managed, and we really means, well, Hill Hopkins, Ravenel, and Kirsten Mazer, and Rolf Hoyer. So that's we, to define a functorial X tensor A for a genuinely commutative G ring spectrum. Okay. And now the next step, I don't need to do any work because I want to do equivariant Loday constructions for genuinely commutative ring spectra A. So you remember what I did when I wanted to do the deconstructions for spectra? Well, there wasn't a group. I just at each level n, I took a, so we start with a simplicial, start with a G simplicial complex X dot. In the old days, it was just a simplicial complex. And then for each n, I took xn, which was a finite set, and I took a tensor of copies of A indexed by that, which is what I now call xn tensor A. But now in the equivariant case, I have a really fancy xn tensor A. So I do that. So for all n, take xn tensor A and get di si by functoriality. And we have a simplicial, a commutative simplicial A algebra. And we're going to call it Lx G A. I call it LXGA because we worked really hard to build GN. Right? But if you forget about the action, then the underlying spectrum is just Lx of A. Right? If you don't get anything to act. And really, there's nothing we need to do. So now I want to say that various known constructions can be written in these terms. The advantage is everything is very intuitive. The disadvantage, of course, if you're willing to assume that A is a genuinely commutative G spectrum. That's the catch. This is the world in which I live. And the two constructions I'm going to say don't require all of this. So, okay, I admit this is a disadvantage. So the first construction I want to talk about is, how am I doing for time? Good. Okay, so the first example I want to talk about is G equals cyclic group of order n greater than or equal to 1. And I'm going to look at S1 rot, which is the circle that Cn rotates. Cn is generated by gamma. So, and yes, this is going to be the third appearance of this example. And it's the same example all along. It just, the notation gets fancier every time. So here I take a point x0, and here I have gamma x0 and gamma squared x0, dot, 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 up to gamma inverse x0. And I call this thing E0, and then I have gamma E0 and gamma squared E0, and so on and so forth. Okay, but this is a Cn simplicial set because I'm not going to think of the simplices as points. I'm going to think of them as orbits. So zero simplices can be thought of Cn mod E generated by x0. And one simplices are Cne generated by S0, x0, and Cn mod E generated by E0. And in general, S1 rot in simplicial degree K is equal to Cn E x0k, Cne x1k, Cne xk k, where x0k is equal to S0k times of x0 that I started with, and xik is equal to S0 I minus 1 S1 k minus I of E0. So basically, from now on, everybody's going to be degenerate, and they're going to be either degeneracies of the point or they're going to be degeneracies of the interval. And the question here is how many, like when I go on E0, how many, and I map a I plus 1 simplex into this, how many of the vertices go here and how many go here. So these are all the choices. And okay, so I understand that. So then, therefore, if I do S1 rot K, it's just a bunch of free orbits. So its tensor A is just going to be equal to Cne tensor A, but I'm going to have K plus 1 of them. And what is Cn? So this is the wasteful part. If you do it this way, A should be a genuine Cn spectrum, but if I want to do this, I'm going to forget the Cn action. Okay, so I get N E Cn I E star A, which is why you can do it to any old spectrum. And then I do smash K plus 1. Okay, good. To just get the habit of working with this. And then I know from this description that dj of x0 k is equal to x0 k minus 1 for all j. That's the thing that's degeneracy on a point. And then I have dj xik is equal to xi minus 1 k minus 1 or xi k minus 1. It depends. This is if 0 less than or equal to j less than or equal to I minus 1. And this is if I less than or equal to j less than or equal to k, but I is not equal to k. And then we have the special case dk of x kk, and that is gamma inverse of x0 k minus 1. That's the interesting one. So what I'm saying is, what if I had this degeneracy of E0 that sent k vertices to here and only the last one to here? And then I threw out the last one. Then I am here, but I am here, I'm not here. And that's why I take gamma inverse. So this gamma comes from the structure of the simplicial set and affects this thing. Because what's going to happen is, okay, so this is just the structure of my simplicial set. Okay, so I have this. So what do di NECN IE star a k plus 1 into NECN IE star a k, what do they do? So I'm going to write all these norms vertically. Okay, so each of these is the norm. And basically I'm saying that di, take the copy of the norm corresponding to xi and send it to this. So basically what's going to happen is this copy is going to go to the 0th copy. This copy is going to go to the first copy. The ith copy is going to go to the ith copy. The I plus 1th copy is going to go to the ith copy. So two adjacent copies are going to be multiplied. And that, okay, so that's going to be, it just multiplies column I and column I plus 1 for all I less than k. Okay, what does dk do? Dk wants to take, so these columns all stay where they are. This column wants to go to the 0th column, but it has to be acted on by gamma inverse. Gamma pushes the coordinates down, gamma inverse pushes them up. So it takes this guy, or maybe I said it opposite. Gamma inverse should take this guy and put it in the front, and everybody else gets pushed down. Okay, so I need to jump to the other side, which is unfortunate, but okay, so dk takes last column. Puts this one in the front, and then, so this is the gamma inverse, and then multiplies with 0th column. So this is something that, so Angelt-Zweit, Blumberg, and Gerhard and Hill and Lawson and Mendel, they define for B a genuine a probably they just need algebra in genuine commutative in genuine CN spectrum. They define T relative THH relative to CN. So they look at something called THH, so it's THH CN of B, and at level N, what they want to take is B smash N plus 1, and so DI for DI from B N plus 1 to B N for I less than N is the THH. DI, you just take the ith B and multiply it by the I plus first B. But the last one, Dn, acts on last B by gamma inverse and then multiplies into the 0th one. And so what I just showed that if you want to do my definition of LCN of S1 rot of A, what you get is their THHCN of NECN IE star A. Because that's exactly what I did. I acted by gamma inverse and then multiplied. This is tautology. I'm not saying anything interesting. Okay. In their case, it was really interesting because what Viglic and Co. A, B, G, H, L, M, what they were actually doing is they were saying that THH of B, and now B doesn't have any action. So what it is it should be thought of as the norm from E to CN. From E to S1. So that's something we haven't discussed. Lie groups, compact Lie groups, not finite groups. Okay, of B. And the way they think about THHCN of some, okay. Now, okay. This is just a spectrum. This is a genuine CN spectrum. So they say you should think of it as NCN S1 of B. And they would interpret the result is that if you apply N CN S1 to N E CN of C, you get NE S1 C, which is what you're supposed to get. So that's how they write this. Okay, so I have a construction. It includes the relative topological Hochschild homology of all these people. What is it really? So there was the wasteful thing that I had some CN structure on A that I threw out. But if you think about it, if I take the last one here, I put it up and I write this. Basically, what I've just done is I have done SDR of THHA written as a matrix. Originally, I had a long line, and the DI just took adjacent guys, which is exactly what happened. So here, assuming you read this the usual way you read, and the di just multiply in all the different places. And what does the last one do? Okay, the last one, it gets like this guy suddenly goes into this guy. This guy, because this guy pushed it down, it suddenly goes into this guy. This guy goes into that guy, and so on. It is just SDR. It's the same. So if you start with CN action on A that you're willing to throw out, the SDR, the CN action on SDR, which the CR action on SDR, which you're interested in, is this fancy thing. Okay. Okay, so that's good. And maybe I'll erase here. And another example is x equals S sigma, the flipped circle. So there's 2 points here that are fixed, and 2 point at 0, point at infinity. And the C2, G is equal to C2. And it flips these. This is a C2 simplicial complex. And the zero simplices, here I have 2 kinds of orbits. The zero simplices are C2, C2 that's called 0, and C2, C2 that's called infinity. And the one simplex is degeneracies of these two. I'm going to call this maybe E. And C2E. Oh, okay. That was really funny. Okay, let's not call it E. Let's call it, okay, X1. And C2E times X1. And the big calculational paper of, and this is of course what real THH is based on. The big calculational paper there is Dotto, Moy, Horia, and Ray. And of course, they don't assume commutativity. They just take a spectrum with anti-involution. This I lose, I agree. But they show that THR, under very minor assumption, THRA can be thought of as B A N E C2 A and A. And in this notation, it's very obvious, because this A is this point, other A is that point, and then you have the edge between them, and of course then you have all the degeneracies in the edge between them, which gives the bar construction. So we exactly see what happens. Okay, so those are the 2 examples that I wanted to talk about of Loday constructions of G equivariant spectra, which give me G simplicial spectra. I do think it's an intuitive way of doing it. The problem with that is that, okay, so calculating this thing is hard. So of course, non-equivariantly, THR, this is just a simplicial complex whose realization is S1. So if you look at the fixed points of the trivial group, pi star of THR itself is just THH star. It's what we know. But interesting things you could do is you could try to look at pi star of the fixed points, pi star of the geometric fixed points, the ROG graded homotopy groups. So the moment you start taking into account the action, it becomes harder. So the problem is it's calculations are hard. And DMPR, they did a lot about HFP and HZP. And we had a talk of Abhinandan, who talked about tone spectra and their THR. But, right, and hopefully there'll be more calculations of this as time goes by, but it would be nice to have an easier problem. Okay, so motivation. Let R be a ring spectrum, an algebra over the sphere spectrum. I can map a connective ring spectrum. I can map THHR, the simplicial spectrum, into the simplicial abelian group HH of pi 0 R by linearization. At each simplicial level n, I'm going to map R smash n plus 1 because it's connective. If I apply pi 0, I'm going to get R tensor n plus 1. This is pi 0 of that. And this behaves well with respect to the di and si. So this gives me a map from THH star of R. It's called linearization of HH star R, and it's usually not surjective or injective, or it's not the greatest map in the world. Nevertheless, this is a thing I can calculate. And in calculations of this, you try to calculate the abelian groups that are THH star of R. Often in the last stage, when you're trying to get the multiplicative extension data to understand this as a ring, this comparison map can be useful. Often. Anyway, it's just thing that exists. So, good. So I want to do this. Want to do something. Analogous for genuinely commutative G ring spectra. And the obvious the monoidal structure. So this is Loday. So now I'm going to take Tambara functors, and they also have, I forgot to say, this square product.
Square.
This thing, yeah, that we had from Mackey functors, it extends to Tambara functors, and I forgot to say this. And A remains the, okay, I guess it has to. A remains the unit for that, yeah. So I exactly want to, right, so pi 0 underline would go from such a guy to Tambara functors. I forgot to say this. Okay, I don't know where it's hid in my notes, but yeah, okay. So okay, so we're talking about Loday constructions of Tambara functors. And Tambara functors also have Eilenberg-MacLane spectra HT. And that's John Ullman showed that. And the product we had on Mathy functors also worked here. So I had this flippant definition. I don't want to give you a definition. So I'm just going to say that T square S can be defined as pi 0 underline of T HT smash H S. Right.
You are only thinking about the structure as a commutative thing.
Well, no, but no, it actually does. No, I don't. This actually does. If you have a Tambara functor, then you could give HT the structure of a G ring spectrum. And then you could do this. And in fact, this is going to be.
You are just using the box.
If we just, no, we shouldn't, because we do want, like when we do the DI, we do want to take T box T and map it to T. So no, I'm not forgetting. I'm just skipping details like mad, but no. And I'm doing the same cheat, but it's much harder this time. Yeah. Okay. And we already announced, really, that I basically, moreover, I can define for X a G simplicial set G tensor T. Sorry, for X a G set. Let's talk about this. I can define G tensor T to be the same cheat. Oh, this is X. Okay, that's why it looks weird. X tensor H T. So you're saying, why is this easier to calculate than this? The point is that there are formulas for it. Point there are formulas for M n. And basically, but to answer your question, if I have
A X box.
Well, no, I define, I'm defining boxes for, no, I mean, it doesn't somehow work with categories. So I mean, this thing is no, it's a spectrum rather than a simplicial set. So it's too big. No. So this thing is a genuine spectrum, and then this thing is a genuine spectrum, and then pi zero underline. Okay, so this looks like a cheat, but the point is, and this is also a cheat, it sort of cancels. There are formulas for M box N or T box S with T and S Tambara functors. And actually the reason they're not so bad is they actually, like the box of two Tambara functors is the box of the underlying Mackey functors, except there's a product and all the extra structure on it. So like the equation I wrote for the box product in the CP case, it works here. And for easy norms, so for example, so I'm doing this out of laziness not to write combinatorics, but for example, if G equals e.g., if G equals CP and H equals E, and S is a commutative ring, which is the same thing as an E Tambara functor, then I can tell you NECPS at level E is just equal to S tensor P, and CP cycles the coordinates, and NECP of S at at CP, yeah. It's a strange thing. It's combinations of elements of S with coefficients in Z. So each of them has a bracket to denote the generator corresponding to it. So this is a big direct sum of Z's plus S tensor CP modulo CP with this action that we talked about here. And by the way, if you take a generator corresponding to A and a generator corresponding to B, their product is the generator corresponding to AB. There's a formula to say how you, here you multiply the obvious way. There's a formula not hard about how you multiply this and this, but there's also a relation where the generator corresponding to A plus B is equal to the generator corresponding to A plus the generator corresponding to B. This is very similar to what we did before, and not by accident. Sum of all equivalence classes under rotations of words like A tensor B, tensor A tensor A, tensor whatever, with at least one A and at least one B. It comes from the previous, that's why it's the same, right? So I'm looking at, so these words have to have at least one A, at least one B, and CP rotates on them, and I take one representative of each coset, and this lives here. So the point is that although I define it in this cheating way, this is actually a lot easier to calculate than the actual Loday construction. And no, okay. Yes. No. So the point is that there actually is a way of officially defining box product of Tambera functors. There is a way of officially defining norms. Just the combinatorics are very complicated. But if G is equal to CP, it's not so bad. But it gives me, but it agrees with this, yes. And then the point of all this, okay, I don't have, and then I can consider LXCN of A, and I can consider, and this is a Loday construction of equivariant spectra, and I could look at LXCN of pi 0 A. So this is a Loday construction of Tambera functors. And I can have a linearization here that's exactly patterned on what I did in the non-equivariant case. So what I'm going to get is I'm going to get a function from pi 0 of LXCN A H into LXCN pi 0 A applied to H. And what is this thing going to be? This is going to be a simplicial Tambera functor. It's going to be a simplicial array of things that accept. So if you feed everybody up the chain A, you get something that this maps to, and it's a kind of linearization. It goes for all the H's in G. And there was an example that Birgit Richter and I calculated. Okay, skipping stuff. We looked at S sigma C2. So S sigma is the guy from THR. And we applied it for our fix, where R is a commutative ring with involution. We generalize the result then by getting rid of commutativity, and then we wanted an anti-involution here, but that went outside the Loday world. Half is in R. So we look at this, and of course we know that if we do L S sigma C2 of R fix at E, we just get Hochschild, the Hochschild complex of R. But if we do L S sigma C2 of R fix at C2, and that's the strange one, then we get something called HR star plus Z R R. And this is not for representation homology like Hsiang and Ramadas. This is for reflexive homology. And this was discussed by Graves. And this connects to the beginning talks, because remember, one of my crossed simplicial groups had C2, Gn equals C2 for all n. And the way C2 acts on 0, 1, n is it sends 0, 1, n as it sends 0 to 0 and then flips the order of these guys. So this is a cross simplicial. This is one of the basic examples of crossed simplicial groups. And obviously this does not preserve, it's not simplicial, but the basic crossed examples aren't. So, and each, this is again something we didn't have time to discuss in detail, but if you have the cross simplicial group Cn, there is a construction that associates to the cross simplicial group a homology theory that basically gives you the complex, the double complex for calculating cyclic homology in the case of Cn. In the case of here, it gives you a complex where it's basically R tensor n plus 1 in dimension n modulo 1 minus R, where R A0 tensor A1 tensor AN is equal to, the interesting part is the sine n plus 1 over 2. So it's mod 4 periodicity, A0 bar tensor AN bar tensor A1 bar. So, I mean, this is true if 2 is invertible in R. So like the homology theory, which is reflexive homology, that's associated to this cross simplicial group, in the case where half is in R, it gives you the homology of this complex with respect to D. The funny thing is, these guys obviously mess up with the DI. If you do this sign correction, it does preserve D. So you can look at this complex. That's what it calculates. And there is a choice here if you take 1 plus R or 1 minus R. So plus is when you take a minus. So this is a cross simplicial homology theory of R. And basically the complex we get when we take our Loday construction for R fixed and evaluate it at C2 is quasi-isomorphic to the complex you use to calculate this reflexive homology. So we know what we get at both groups, and I'm out of time, so.
So are there any questions, the speaker?
Can you put pi 0 of x in x tensor HT?
Yeah.
So is that the same as taking the norm with respect to the box thing, or?
Yeah. So I erased it a zillion times, but right. But I'm exactly saying that I want pi 0 underline of x tensor A to be the same as x tensor pi 0 underline of A.
Where this is calculating in the box.
And we can, right, so yeah, so I was joking just for not writing combinatorics that I don't need to write it, but yes, we have specific formulas. They are awful if the group is complicated, but there are specific formulas that give you box product and norms, which is an extra structure. But I wrote this is leftovers from the norm calculation for E and CP. The whole point of this, it's not that close, but the whole point of it is that it is approachable calculationally, as opposed to X tensor A, which is a little scary.
So I guess for T equal to CP, there is a monoidal structure on Mackey functors whose monoids are the number of. I think it's
yeah.
constructed by first and Maser.
Yeah.
So that would work.
So that's the only thing going on. Yeah, that's what's going on. Yeah. There's only one thing happening. Yeah.
But in general, no monoidal structure. No one knows that.
Oh, no, it exists. I mean, I mean, if you don't have a better idea, because of Ullmann and Brunn, you can go back and forth between the nice spectra and the Tambara functors. So if you don't know the monoidal structure here, you can just use the monoidal structure there. So, but just the combinatorics are awful. Like writing down what the box really will be and what the norm really will be is scary. I mean, you could sort of, like in abstract nonsense, you could do it, but if you try to list all the, which is why the Strickland diagrams are, no, I'm sorry, that's just the properties. I mean, the combinatorics, when the groups get hard, the combinatorics gets awful. And that's just the way it is, but it exists.
Are there any other questions?
Restriction transfers and norms or
Oh, yeah.
Loday construction.
Yeah. So this is absolutely Tambara functor, and I can give you the, so what happens here, I can really, in this case, because half is invertible, what this Loday construction does is you could take LS sigma of R and right. No, okay. So you take this guy. This guy is very, very easy. Okay. And then you can take the fix of it level-wise. And this is equal to LS sigma C2 R. This is a lovely example. Sorry. Yeah. It's not generally true. I mean, I'm saying 100 times that it's true because half is invertible and because we showed it and it wasn't totally trivial. No. I mean, our focus of the energy, it's, so the fact that 2 is invertible, it simplifies both the Graves construction and the Loday construction of the Tambara functor. So what we've been putting our energy into is trying to see what we can say if 2 isn't invertible. And I mean, we can sort of say what we have, but yeah, you can write what we have because C2 is not a bad group, but like how to think of it, I don't know. So that's the next thing we've been focusing on and haven't made progress. I mean, again, we can tell you what it is, but we can't really tell you what it is. We could just write equations and tell you what maps are. Which kind? Oh. Okay. Let's see. Yeah, so we did talk some about cotangent complexes. So it's, yeah, but I mean, but somehow when you think about real THH on the flip sphere, and when you think about cotangent complexes, it's not some of this, it's not the same generalization of HH. So it's a little messy. So we haven't I mean, this cotangent complex is interesting question of its own. I mean, you can define the kernel of the multiplication. You can define its quotient by its square, or its quotient by norms, which is not the same. And that is something Mike Hill really wanted to find a distinction between, and we haven't succeeded. But it's a different story. And I mean, you could do stuff, because I would think that intelligent things to be done about it should really be done by looking at the level of spectra and then learning from it. I mean, somehow it's really hard to think about the structure. The Loday construction of spectra, they're horrible to calculate, but they're really easy to think about. And Loday construction of Tambara functors, they're easier to calculate, but much more confusing to think about.
Counter example of I mod I square and I mod norms are not equal. I mean, or written somewhere like difference.
I think there was some rumor that we haven't been able to verify that you cannot find an example where I mod I squared is not 0, but I mod the norms is 0. But we haven't been able to verify it, and we thought about it a little, and then we moved on to this stuff. Yeah, Mike Hill really wanted this, because it is different. It's a very strange world. But it looks more like things we know if you look at it in the spectrum level than in the Loday, in the Tambara functor level.
The other questions? Okay, so yeah, if we have other questions, you can still like talk to Ayelet over coffee.
Oh yeah, I'm here. Yeah.
So yeah, let us thank her for a wonderful series of lectures.